My dear student, today let us talk about Lebesgue integral of a real valued function. We are going to talk about Lebesgue integral of a real valued function. So far we have discussed Lebesgue integral of non-negative measurable function. So how we define, let us just recap how we define the Lebesgue integration. First we define Lebesgue integration of a simple measurable function, non-negative simple measurable function. So pi, this, let us see. So this phi denotes non-negative measurable simple function. So integration of this function is defined by summation. So I is running from 1 to n ai, a measure of this ai. So simple function means what? Function phi is equal to summation I is running from 1 to n ai and characteristic function chi ai. This is your simple measurable non-negative function. These are all non-negative. So integration, Lebesgue integration is defined by this one. Then from this we extend the definition to a non-negative measurable function. So f is a non-negative measurable function. Then how we define? There are two definitions. The first definition is that integration of such non-negative measurable function f is defined by this formula. This is equal to supremum of phi, which is less than equal to f integration phi dx. So consider you take all the simple measurable function which is dominated by f, and you take all the integration of such simple measurable function. Then you take the supremum of such simple measurable integration. Then that is the integral of this one. So later on we prove Fatau's lemma, then monotone convergence theorem for non-negative. Then this is the second definition. The third definition is equal to what? Integration of a non-negative measurable function f is defined by this formula. Integration, so limit integration, say phi n dx. Alright, where phi n is a sequence of simple measurable function which is monotonically increasing to the function, increasing and converging toward a function f. Okay, so this is a sequence of simple measurable, non-negative simple measurable function which is monotonic increasing, means phi 1 is less than equal to phi 2, phi 2 is less than equal to phi 3, like that. It is monotonic increasing and converging to the function f, and then this integration is equal to this one. So this is the definition. So far we have defined Lebesgue integration of non-negative function. The only thing we are assuming here is f is a non-negative measurable function. But now we want to extend this definition to any function, means it can take negative value also, positive value also. Okay, so that is the thing. So far we have done Lebesgue integration of non-negative function. From today we are going to extend this definition to any real valued function. That means it can take negative values also. Okay, it can take negative values also. That is all about today's lecture. This is the beginning of integration, Lebesgue integration of any real valued function. We are not giving any measurable real valued function. We are not giving the condition that non-negativity. Okay, so and that is the beginning of real valued function Lebesgue integration. That is why it is important. First concept we are going to define. Later on we will be giving some result theorems, all these things. Okay, so the important definition is very important starting point. So we know the integration of a non-negative function. So given a real valued function r, as a f is any real valued function, then we define f positive x is equal to maximum of f of x and 0. Okay, if f of x is negative, then maximum value will be 0. If f of x is positive, then maximum value is f of x, because it is the maximum of f of x and 0. And then f positive x is always non-negative. Okay, it is non-negative, it is either 0 or positive number. Similarly, f negative x is defined by this formula, maximum of minus f of x 0. If f of x is positive, then minus f of x is negative. Maximum of a negative number and 0 is 0. So the maximum value is 0 here. If f of x is negative, then minus of f of x is positive. The maximum value of a positive number and 0 is positive. So in all possible cases, this f negative x is never negative. Okay, it is either 0 or some positive number. So now, given a real valued function f of x, we define f positive x and f negative x like this. And from the definition, it is very obvious that f positive x is never negative, f negative is never negative also. So this function f positive x and f negative x are said to be positive and negative parts of function f of x respectively. Okay, so this f positive x is the positive part of the function f of x, and f negative x is the negative part of the function f of x. Okay, so given a function f of x, this is real valued function, we can define two non-negative function f positive x and f negative x. Okay, given a function f of x, we have defined two non-negative function f positive x and f negative x. If f of x is measurable, if f of x is measurable, if this function is measurable, and the 0 function is also measurable, so this function is measurable, that means f positive is also measurable. Similarly, if f of x is measurable, minus of f of x is measurable, so maximum of minus f of x and 0 is also measurable. That means f negative is also measurable. So whenever the function f of x is measurable, the positive part f positive x is also measurable, the negative part f negative x is also measurable. Okay, so this is the thing we have. This is very straightforward from the definition. All right, so then let us give this small result. Given a function f of x, it can be written in the form in its positive parts. Okay, the f of x is equal to f positive minus f negative, and modulus of f is equal to f positive plus f negative. And from the definition, it is obvious that f positive and f negative, they are all non-negative. Okay, non-negative, because why? We know the integration of a non-negative function, Lebesgue integration of a non-negative function. So given a function f of x, we have defined two non-negative functions. So in this non-negative function, integration is well defined, because according to the definition we defined so far. Okay, so we are going to use this concept and defining integration of any real valued function. Okay, that is the whole idea. The first, let us establish this small result. It is very straightforward, but for the sake of simplicity, let us prove it so that you can understand. So we want to establish this one, f is equal to f positive minus f negative. So when f of x is equal to 0, if f of x is equal to 0, f positive x is the maximum of 0 and 0, that is 0. So whenever f of x is equal to 0, f positive x is equal to 0. Similarly, whenever f of x is equal to 0, maximum minus 0, 0 is 0. Okay, so f negative x is equal to 0. So f negative x minus f positive x minus f negative x, 0 minus 0, that is also 0. Okay, so the function f of x is equal to 0 minus 0. So that is true. Okay, that means when f of x is equal to 0, this equality holds true. Okay, when f of x is equal to 0, this part f of x is equal to 0, f positive is also 0, this is also 0, so 0 minus 0 is 0. So whenever f of x is equal to 0, f is equal to f positive minus f negative, this equality holds true. Now let us consider the case when f of x is positive. When f of x is positive, then what happens? f positive x is equal to maximum of f of x and 0. Since f of x is positive, the maximum value will be f of x itself, this one. So how about f negative x? This is equal to maximum of minus f of x is 0. So f of x is positive, minus of f of x is negative. So maximum or negative number in 0 is 0. So in this case, this one. Alright. So this is f of x and this is 0. And therefore, f positive x minus f negative x is equal to f of x. Alright. So here also it is true. When f of x is positive, this equality holds true. This one. When f of x is positive, this is f of x, this is 0. So f of x is equal to f positive x minus f negative x. That is true. So the case when f of x is positive is true. Right. Next, let us consider the case when f of x is negative. So when f of x is negative, what happens? When f of x is negative, f positive x, this is f of x, okay? This is f of x, there is no sign. So when f of x is negative, maximum of f of x 0, this is negative, so maximum of some negative number and 0 is 0. Alright, so therefore f positive x is 0. So how about f negative x? F negative x is equal to maximum of minus f of x. This is minus f of x and 0. So f of x is negative, so minus of f of x is positive. Alright, so maximum value will be minus f of x. This is the minus f of x. Okay, so in this case also, 0 here, then here minus f of x, then it is equal to f of x. So whenever f of x is negative, f of x is equal to f positive x minus f negative x. So in this case also, f is equal to f positive minus f negative. So in all possible cases, the equality holds true. That is what? In all possible cases, f is equal to f positive minus f negative. Okay, so we have established. So what is the ultimate thing you have to take? The ultimate thing is that the given function f, which is negative also, which can take negative value also, positive value also, this can be decomposed into two positive functions. This function minus this function. Okay, both are non-negative function. Okay, so this real valued function can be decomposed in this form, that f positive minus f negative. But we know that f positive is non-negative and f negative is also non-negative. All right, so integration, this is well defined, because if this is measurable function, this is non-negative measurable function. For non-negative measurable function, so far we have developed so many theories of Lebesgue integration, and this is also non-negative measurable function, so this is also well defined. Okay, so in those values we are going to define the Lebesgue integration of a real valued function. Okay, so number 2, let us establish number 2. What the number 2 says, that modulus of f is equal to f positive plus f negative. Okay, modulus of f is equal to f positive plus f negative. Okay, so when f of x is equal to 0, what happened? Then f positive is also 0, because maximum of 0 and 0 is 0 itself. So this is 0, and f negative is also 0, because maximum value of minus 0 and 0 is 0 itself. Okay, so therefore the modulus is also 0. Whenever the function is equal to 0, its modulus is also 0. So this equality holds true. Okay, this part is 0 and this part is 0, so they are equal. So when f of x is equal to 0, f modulus is equal to f plus f negative. This is true. So let us consider when f of x is positive. What happens when f of x is positive? So in this case, then f positive is equal to f of x. The maximum value of f of x and 0 is f of x, because f of x is positive. And what about f negative x? The maximum value of minus f of x and 0 is 0, because f of x is positive, minus of f of x is negative, so maximum of some negative number and 0 is 0. All right, so in this case also, modulus of f of x is equal to f of x. Okay, modulus of a number, if it is positive, it is the number itself. So therefore this part is f of x and this part is f of x and this is 0. Therefore modulus of f is equal to f positive plus f negative. This equation holds true whenever f of x is positive. So next, let us consider the case when f of x is negative. So when f of x is negative, then so maximum of some negative number in 0 is 0. Alright, so f positive of x is equal to 0. So when f of x is negative, maximum of minus of f of x 0 is minus f of x, because f of x is negative, minus of f of x is positive, so maximum value will be the positive number. So this is true. Then what about if f of x is negative? From the modulus function we know that modulus of f of x is equal to minus of f of x. This is true. So in this equality you see whenever f of x is negative, this part is minus f of x, this part is 0, and this part is minus f of x. So in this case also modulus of f is equal to f positive plus f negative. This equality holds true. Okay, so in all possible cases we have proved that, we have established that modulus of f is equal to f positive plus f negative. Okay, all right. So any real valued function, its modulus is equal to its sum of the positive part and plus sum of the negative part. Okay, sum of the positive plus part plus negative part. Okay, this is all about. So what is the thing you have to remember? Given any real valued function, so it can be decomposed into two parts. One is positive part, another one is negative part, and the function is equal to positive part minus negative part. Okay, so that is what we have just proved. Again, modulus of the function is nothing but sum of the positive part and negative part. That is the modulus of the function. Okay, so and then it is very straightforward. If f of x is a measurable function, then f positive is also measurable, f negative is also measurable. F of x, because modulus of f of x, they are also non-negative measurable. This is non-negative, this is non-negative, this is also non-negative, so they are all non-negative measurable function. So given a real valued measurable function, we have defined three non-negative measurable function: f positive, f negative, and modulus of f. Why they are measurable? Because earlier we have proved some result. What we prove is that, let's just recall, if a function, what we prove, it is blurred, why I don't know, let us see. So if f is measurable, what we do is that if if f is measurable, if f1 is measurable and f2 is also measurable, the supremum or maximum of 2, this is equal to maximum of say f1, f2. Why it is very blurred? Let me open another window. So what is that? If f1 is measurable, f2 is also measurable. This is supremum, or for finite case it is called to maximum. f1, f2 is measurable. This function, this is a new function f, this is measurable. That is what we have learned so far. So in this case, if you take this one, supremum f of x and a 0 is a 0 function, this is equal to maximum of f and 0. So this is equal to what? This is equal to f positive. So f is any measurable function, then 0 is also constant function, so its maximum, that is f positive, is measurable. So and what we have developed is that f positive is a non-negative. This may be negative, but f positive is a non-negative function, and if f is measurable, from this f positive is also a non-negative measurable function. Similarly, maximum of, if f of x is measurable, then minus f of x is also measurable, so this is equal to this is f negative. Okay, so if f of x is measurable, it is any non-negative, it is any measurable function, real valued function, then f negative is also measurable, but the thing is that this is non-negative and this is also non-negative. Okay, and then if f is measurable, then from this what we have, f positive is also measurable and f negative is also measurable. Okay, and therefore what, this modulus function is the sum of two non-negative measurable function, therefore it is also measurable. Okay, so given a real valued measurable function f of x, given a real valued measurable function f of x, now we are defined two non-negative measurable function. The first one is f positive, the second one is f negative, and the third one is modulus of f. They are all non-negative measurable function. Okay, so that is what we have just developed. Okay, so next let us go. Now then let us define what is the integration of a non-negative integration, Lebesgue integration of a real valued function. Okay, integration of a real valued function, let us define. So if f is a measurable function, so it can be negative also, measurable, and so if f is measurable, f positive is a non-negative measurable function if it is if its Lebesgue integration is finite. Also, if f is a measurable function, then f negative is a non-negative measurable function. For non-negative measurable function, we have already defined the Lebesgue integration, so this is well defined. And if it is less than infinity, both this non-negative function f positive and f negative, they are integrable according to the theory we have developed so far. If their Lebesgue integration are finite, then we say that f is integrable. In that situation, what we say, f, this is measurable function, is said to be integrable, and its value is equal to difference of these two. Okay, so this is finite and this is also finite. Difference of two finite number is well defined. If one of them is negative, okay, then it is not defined. If both are if both are infinite, yes. If both are infinite, then it is not defined. Since both are finite, then their difference is defined. If this is infinity, if this is also infinity, infinity minus infinity is not defined. Therefore, we are we are giving restriction to the finite case only. If both are finite, this difference is well defined, and this difference is nothing but the Lebesgue integration of f. Okay, so how we define the Lebesgue integration of a measurable function. So first you define the positive part of the function, that is a non-negative measurable function, okay, f positive, and then you define the negative part of the function, that is f negative, that is also non-negative measurable function. Their integration is well defined. If their integration are finite, it's the differences, f positive and f negative, its value is called the Lebesgue integration of the function f. Okay, so this is how we define Lebesgue integration of any measurable function. All right, just you think about the positive part and negative part, take their integration, they are finite, then their difference is the Lebesgue integration of the function. Okay, so this is how we define the Lebesgue integration of a measurable function. Okay, so let us see if f of x is integrable, then from the definition, what is the requirement? If f of x is integrable, then the integration of the positive part is finite. Integration of the negative part is also finite. That is directly coming from the definition. Okay, then what happened? But what happened? Modulus of f is, we know that it is equal to f positive is equal plus f negative. Okay, this is negative, f positive is a non-negative measurable function. This is also a non-negative measurable function. So sum of the function, two non-negative measurable functions, their integration is equal to integration of the first function plus integration of the second function. This theory we have developed so far. Okay, for the non-negative measurable function, these are sum of two non-negative measurable function, their integration is equal to integration of the first function plus integration of the second function. But this sum is nothing but your modulus function. So the integration of the modulus function is equal to integration of the positive part plus integration of the negative part. All right, this is very straightforward from the definition. Okay, so then what is the, what is the thing you have to remember? If f is integrable, then modulus of f of x is also integrable. Okay, and conversely, let us see if modulus of f is integrable. Okay, so then according to this definition, f modulus positive part is finite. Okay, so what is f modulus positive part? That is the modulus f of f. Okay, modulus, this is positive. Okay, this is finite. All right, because why? This one you can modulus of this one. Let us go back to the another window. So for any function, what is f of f positive? This is equal to maximum of f of x and 0. So what about the modulus? Its positive part is equal to maximum of, this is the modulus f of part. Okay, so this is, since this is always positive, what you get, this is equal to f of f, right? So that is the thing, so according to the definition we have defined so far, f positive is integrable, means it's, modulus of f is integrable, means it integration of its positive part, that is modulus f positive, is finite, integrable. Okay, so but modulus of f positive part is nothing but it is the modulus of f. This is finite. So this is finite means what? So since this is equal to sum of the non-negative function f, f positive and f negative, they are equal. So this is finite. All right, so if the sum of two number is finite, they are individually finite. So this is finite, this is finite. So integration, Lebesgue integration f positive is finite, Lebesgue integration f negative is finite. Their difference is nothing but the integration of the function f. So it is defined. Since they are finite, this difference is defined. That means Lebesgue integration of the function f is defined. So what is the thing you have to remember? Then a function is Lebesgue integrable if and only if its modulus is integrable. All right, if and only if its integration is integrable. So these are the elementary part. We are now coming to the new territory, that is integration of a real valued function. So earlier we defined integration of a simple function. From simple function we extend the result to the integration of a non-negative measurable function. Now today we are defining integration of any real valued function. Okay, so how we do this? We define the positive part of the function, then we define the negative part of the function. Then it is obvious that the function is equal to difference of the positive part and negative part. Okay, for the positive part we already know the Lebesgue integration. For the negative part also we already know the negative the Lebesgue integration. So if the Lebesgue integration of the positive part is finite, Lebesgue integration of the negative part is finite, their difference will give you the Lebesgue integration of the measurable real valued function. So this is the starting point. We are going to extend all the result we so far we have done for the non-negative measurable function to the real valued measurable function. Okay, so this is the definition. I think it is better for you to understand it. You try to do it yourself, definition. you write, you read it, watch it. Okay, so next day we are going to give some more elementary results. So this much I want to give you today. Okay,